Hi there, my name is Mike Pleasance from the Hertzberg Astronomy and Astrophysics Research Center of the National Research Council of Canada. And I'm going to be giving a talk on the Trident frequency slice architecture, correlator and beamformer reference design that we did for Ngvla back in 2018. So the outline for this talk, first I'll quickly cover the requirements for the Ngvla correlator beamformer, and then give an overview of the frequency slice architecture that was created for the SKA mid-correlator beamformer. Go into a little bit of information on the Talon DX FPGA board and the Talon LRU that was developed again for the SKA correlator and used as the basis of the reference design. And finally, get into the design of the Trident CBF that was submitted for the Ngvla correlator reference design. So the key requirements, correlator needs to be able to handle 263 dual polarization antennas, 20 gigahertz per polarization of instantaneous bandwidth coming from the antennas and being processed for imaging. Also a variety of beamforming functionality, including 10 pulsar timing beams, 10 pulsar search beams, and 5 VLBI beams. And during simultaneous observation modes, there needs to be 28 gigahertz per polarization of aggregate bandwidth that can be generated across all the various data products by the correlator. Finally, the maximum baseline length is 10,000 kilometers. So while working on the SKA1 mid correlator, it was a very challenging problem because SKA mid has 6 different bands at 3 different sample rates, and the original requirements and design required full flexibility across subarrays, essentially meaning that any subarray could be operating in any band, and all of them could be operating in any of the many combinations of different observing modes for imaging and beamforming and things like that. So this led to a very complicated and expensive correlator, and the frequency slice architecture was proposed to the SKA office in early 2017 as a way to save some cost. And it still provides the full bandwidth for correlation and beamforming, but not necessarily everything at the same time, and not with complete subarray independence. So switching to this approach vastly reduced the number of FPGA designs and the complexity of them. It also cut the hardware in half, which had significant cost savings and also reduced the power. This was accepted by the SKO and incorporated into the design baseline, and is the current design of the mid correlator beamformer. So for the frequency slice architecture, essentially the processing is split into 2 parts. There's a VCC, or very coarse channelizer part, which is where all of the band-specific processing is done, and this splits the digitized band into a set of 200 megahertz oversampled, evenly spaced frequency slices. And then these frequency slices are distributed to a number of frequency slice processors, which gets the same frequency slice for all of the antennas, and then it performs one operation, which for SKA mid can be either correlation, pulsar beamforming, for pulsar search, pulsar timing beamforming, or VLBI beamforming. So this just shows the how the 26 frequency slice processors for the SKA mid correlator can be used for various observing objectives depending on what band things are operating in. So you can see in the lower bands where there's not as much instantaneous bandwidth in the digitized band, there's lots of frequency slices available for both imaging and also for zoom windows and pulsar beamforming. And as you get up into band 5, where there's 5 gigahertz of instantaneous bandwidth available for imaging, if the full bandwidth is being correlated, then that's using all the FSPs and there aren't any available for other functions. And if in band 5 you want to be doing pulsar beamforming or VLBI, it needs to be traded off against correlation for imaging. So this graphic shows the frequency slice architecture tailored for NGVLA. So we have 263 very coarse channelizers that generate a bunch of frequency slices that can be distributed to any one of the 50 frequency slice processors, which then generate data products that go downstream to the archive or a science data processor or whoever needs to use them. This slide just shows how for simultaneous observing modes, a single frequency slice can be distributed to multiple frequency slice processors. So if you wanted to be doing imaging and VLBI or pulsar search or timing beamforming on the same slice of the same frequency slice, then you can do that by distributing that to many frequency slice processors. So the reference design is based on the technology we've developed for the SKA1 correlator. This is the Talon DX FPGA board, which has a Stratix 10 SX280 FPGA on it, and that includes an embedded ARM processor on the FPGA for monitoring control. It's got 4 DDR4 DIMMs and a whole bunch of optical I/O, 5 12-channel bidirectional FCI LEAP midboard optical modules. They can run at 26G per channel, and 2 QSFP28 cages for doing 100 gigabit Ethernet. It's an air-cooled board with a stacked fin heatsink, and we put 2 Talon DX boards in each Talon LRU, and that's a custom server that's 2U in height. This is a block diagram showing the major systems on the Talon DX board, and for anyone interested in looking at it in more detail, feel free to pause the video, but I'm going to move on. This is a picture of the first prototype of the Talon DX board we received in August of 2017, and another picture showing the Talon LRU with 2 Talon DX boards. And a note that SKA requires air cooling, but this is certainly amenable to liquid cooling, which could potentially reduce the height of the box to 1U. So for the reference design for NGVLA, we came up with something called the Trident CBF design, and it leverages a lot of work done on the SK1 mid CBF correlator. And we did this because the main goals of the reference design was something that was low technological risk and high cost certainty. And we were able to do that by adapting the SK mid correlator that a lot of work had gone into. So now the other note is that the frequency slice architecture and the Talon technology is well suited for this task if we were building it today, but likely with NGVLA construction not starting for a number of years, there will certainly be new technology nodes that the real solution will be based on. So the high level design is that we have 3 Tridents that can process 10 gigahertz per polarization each to give 30 gigahertz total, so that exceeds the 28 gigahertz of instantaneous bandwidth, aggregate bandwidth. The VCC part in each Trident produces 50 frequency slices, and then there's 50 frequency slice processors that can be configured to do the imaging correlation or beamforming. Across the 3 Tridents, there's 150 FSPs in total, and each FSP can be in one of the modes for correlation for imaging or 4 types of beamforming, which we'll see in a minute. So this is a top level picture just showing the 3 Tridents with data coming in from the DBE subsystem and visibilities and beams going out to the archive or the science processor. And this just shows the signal processing steps where the VCC part is receiving digitized data, doing a wideband delay, and then generating the frequency slices, which are then distributed to a frequency slice processor running in one of these 5 modes with correlation, VLBI, 2 flavors of pulsar beamforming using a true delay, one that generates 4 beams and one that generates 10 beams on a subset of 130 antennas instead of the entire array. And finally, a pulsar beamformer using phase delay beamforming that can generate 100 beams. So in this design for the physical architecture, we may keep the VCC units and FSP units that were used in the SK mid design, but tweak them a little bit for NGVLA. So VCC unit processes 11 antennas and does optical, passive optical meshing to generate a single MGP fiber that has all one frequency slice for all those 11 antennas on it, and then those get distributed to the frequency slice processors. In the FSP unit, which is one frequency slice processor, we receive 26 of these inputs to give all the antennas, and there's 26 FPGAs that do the processing. And it should be noted that the number of FPGAs in the FSP can be increased as needed to either accommodate more antennas or deliver more processing horsepower if it's required. So this is the simplified architecture. It just shows how there's all the 26 VCC units that are processing 11 antennas each, the passive interconnect between there and the FSP units, and then the data product coming out of each FSP. And for each Trident, so this shows one Trident, there are 806 Talon LRUs. So zooming in a little bit to the VCC unit, here we see the 11 Talon DX FPGA boards, which would be in 6 LRUs, one processing each antenna, and them going through an optical circuit, which does the amalgamation of one frequency slice for all the antennas onto one 24 fiber trunk cable that would be connected up to the FSP. And in the FSP unit, similarly, we have 26 Talon DX boards in here with connections back to each VCC unit to receive frequency slices, and then a mesh optical circuit that provides one bidirectional link between each pair of Talon DX boards so that data products can be distributed between the boards for doing correlation and beamforming. So in a single rack, we would assume we would be using a 1U liquid-cooled unit, processing unit that would have 2 boards. So that requires, in one rack, we could fit 2 FSPs and 1 VCC unit, and then the various networking switches we need, and a liquid cooling heat exchanger at the top. And we would need 78 racks in this configuration to implement the entire 3 Trident correlator for NGVLA. And certainly using and the next technology node, the density could be increased even further. So the final thing I wanted to touch on was the cost model used. So there was a lot of work put into the costing for the SKA1 mid correlator, and because for the reference design, we're using the same technology and very similar signal processing algorithms, it was easy to adapt that to various scenarios, and particularly different hardware configurations, sizes of VCCs and sizes of FSPs in terms of number of FPGAs, things like that. And this just shows 2 possible scenarios that were evaluated and how it was easy to roll up the labor hardware costs for various scenarios. So the bottom line is, using current technology, it would be around 130 million US dollars for a correlator using Talon technology. 90 million of that is hardware costs, so it's certainly heavily dominated by the hardware costs, and then labor contingency and a bit of travel. The power estimate for such a system, again using current technology, is around 1500 kilowatts, and next generation FPGAs we estimate would reduce the cost to somewhere between 108 and 120 million, and bring the power down to 900 to 1200 kilowatts based on expected extrapolations of kind of how the last few technology nodes have improved things. So that's a very quick overview of the reference design, the correlator reference design we did for NGVLA, and thank you for taking the time to listen. And if anyone has any questions, please feel free to use the facilities provided by the conference to reach out and ask questions. Thank you very much.